Okay, so this is lesson 2.4, where we're going to be learning about inverses. This follows from the lesson that we had over composition of functions. So remember that whatever is inside here becomes the input into this function here. So we just need to make sure that the letters match. So we're going to take 3 and plug it into the f function, which would be 2 times 3 minus 4. So 2 times 3 is 6, 6 minus 4 is 2, so our answer here would be 2. Again, this would be the input into the g function, and this is the g function up here. So we're going to take 3 plus 2, which is 5. And then this one is just saying, multiply those two outputs together. So we know that f of 3 is equal to 2. And we know that g of 3 is equal to 5. And if we multiply those two together, we get 10. This one is saying that we find what g of 3 is, and then we take that output and we plug it into the f function. So we already know what g of 3 is. G of 3 is 5. So really what we're saying is that we want to replace this with 5. So we're going to take 5 and plug it into the f function. So 2 times 5 minus 4, so 10 minus 4 is 6. And then we want to know what happens if we take g of x, take the x, plug it into the g function, and then take that output and plug it into f. Well, we know what g of x is. G of x is this right here. So we're basically saying we want to know what f of x plus 2 is. So we're going to take x plus 2 as our input, and we're going to plug it into the f function. So we would have 2 times x plus 2 minus 4 equals, whoops, doesn't equal 6. I'm looking at the one right above. Oh, good grief. So this one we have to distribute. So 2 times x is 2x. 2 times 2 is 4, and then the minus 4 just drops down. Well, the positive 4 and the negative 4 add to 0, so we are just left with 2x. So f of g of x is equal to 2x. All right, the inverses today, our objective is to find the inverse of a one-to-one function. So, we've talked about functions before, and if you remember, we talked about functions have unique inputs, which means that the inputs, or the x values, can't repeat. Okay? A one-to-one function, so first of all, if a relationship is going to be one-to-one, it has to be a function first. So the first thing is that it has to have unique inputs, and then the second thing is that it has to have unique outputs. So that means that your y values, or your outputs, can't repeat. Okay? So basically what they're saying is a function is one-to-one if it passes the vertical line test and the horizontal line test. So if a relationship is not a function, it can't be one-to-one. Okay? So in order for a relation to be one-to-one, it also has to be a function. So it has to pass both the vertical test and the horizontal line test. It's unique, its inputs have to be unique, and its outputs have to be unique. We're not going to do this example. I'm going to show you a couple of others. So first of all, what this graph wants us to find first is this graph a function? So remember, the easy way to tell if something is a function is just to take a vertical line and to pass it across the graph of the function. And if your line touches the graph at only one point every single place on that line, then we have a function. So this, yes, is a function. The way to tell if that function is one-to-one is to pass a horizontal line across your graph. Now, if you notice, this horizontal line touches the graph here and here at the same time. So because this line here touches this line 2 times at the same point, this cannot be one-to-one. Okay, it does not pass the horizontal line test. So the outputs for the output for 1 would be 4, and the output for 5 would also be 4. So your inputs are unique, because your inputs never repeat, but your output repeats. So 2 of your inputs have 4 as the output. Okay, this one wants us to use graphs to determine which functions are not one-to-one and which functions are one-to-one. So what I've done is I've graphed all of these, and I'm doing this wrong, so I have to do a desktop annotate. Okay, so this is the first graph. This is the graph f of x is equal to x. Okay, so if we take a vertical line and a horizontal line, first of all, we know that these are all going to be functions. So that's what they're telling us, that all of these are functions. Okay, we want to know which of these functions are not one-to-one and which of them are one-to-one. So the only thing that we have to do is the horizontal line test, because we already know that they are functions. So if we take this horizontal line and we pass it across this graph, we can see that that red line doesn't cross the blue line more than once at any spot. Okay, if we take the same horizontal line and we pass it across this one, we can see that any place along here, you have an intersection with the red line at 2 places. So this one, x squared, is not a one-to-one function. So the first one, yes, was one-to-one. X squared is not one-to-one. Okay, the next graph that we have is the graph of x cubed. Okay, so again, if we take this graph, or this straight line, horizontal line, and pass it across the graph, we can see that it doesn't cross at any point more than once. Okay, so our graph of x cubed is one-to-one. Okay, so here's the graph, 1 over x. This is our graph right here. This is our function. So if we pass this over, this one is a little bit hard to see. And it might help if we bring the table up to see this one. Okay, if you look at the table here, this column right here represents the outputs in that table. And if you notice, there are no repeats, okay? And that's the definition of one-to-one, that your output can never repeat. You should have a different number for every single input on your table. Okay, so it doesn't matter how far down we go, you can see that these are not repeating. They're very close, but they are not repeating. Okay, so this graph is one-to-one. Okay, the next graph that we're going to look at is, I don't know why there's a 4 there. It should just be absolute value of x. The 4 just makes it skinnier, so you can imagine that your answer would still be the same. But if you notice, the graph crosses here, or the straight line, the horizontal line crosses here.
Kennedy Johnson, your right is here. Kennedy Johnson, your right is here. Thank you.
process here and here, so this cannot be 1 to 1. No. Okay, the next one is the graph of, oops. Oh. Let's get this to work now. There we go. And I might slide this over a little bit so we can see it better. Okay, so this is the graph of square root of x. So again, if we take our horizontal line and slide it down, we can see that it's not touching any point more than once. So square root, yes, is 1 to 1. Next one we're going to look at is x cubed minus x, and then we'll look at x cubed plus x. So this is x cubed minus x. And we should already be able to tell, once we get down to this point right here, no, this is not 1 to 1. But if we do x cubed plus x, yes, this is 1 to 1. So no, yes. All right, so an inverse function has the following properties. We say this f inverse. F inverse has domain B and range A. If you think about our normal functions, f has domain of A and range B, okay? So for any x in your domain, your function and your inverse cancel each other out, and what you're left with is the input. Okay? So here's what you really need to understand about functions, or about inverses. Your domain and your range are switched. So that means that your input and your output are switched, which means that your x's and your y's are switched. Okay? Your x and your y are switched. To find the inverse of a function, you switch around your x and your y and you solve for y. So if we want to find the inverse of the following, okay, the very first thing that we have to do is we have to take the x and the y and we have to trade places, okay? So the very first thing that we do is we take x is equal to 3y minus 1, and then we have to get y by itself. So we need to add 1 to both sides. And I like to put mine in between here. So x plus 1 is equal to 3y. And then to get y completely by itself, I need to divide each term by 3. So now I have y by itself. And the way that I would write that is I would write f inverse of x is equal to x over 3 plus 1 over 3. So these two functions right here are inverses of one another. All right, this function right here can be rewritten. This f of x here takes the place of y. So really what we're saying with this one is y is equal to 1/2 x plus 4. So the very first step that we want to take when we're finding the inverse is take the y and the x and flip-flop their positions. So we should have x is equal to 1/2 x plus 4. 1/2 y, sorry. Okay. So the first thing that we want to do is we need to get rid of this 4 right here. So we are going to undo that by subtracting 4. So x minus 4 is equal to 1/2 y. And then to get rid of a fraction, we multiply by the reciprocal, which the reciprocal of 1/2 is just 2. And in this case, we need to multiply not just the x, but the minus 4 as well. So when we distribute that, you would get 2x minus 4 is equal to y. So the way that we would write that is f inverse of x is equal to 2x. Making all kinds of mistakes today. That should be an 8 minus 8. Okay, for C, again, this takes the place of y. So really what this is saying is y equals x minus 10 quantity squared plus 7. So the very first step, again, is always just to switch the x and the y. So now you have x equals y minus 10 quantity squared plus 7. So this one is always a tricky one because of the parentheses. So this is what I like to think. I like to go back to this original and think about what my order of operations would be if I wanted to have, say, 3 as my input. Okay? So if 3 is my input, the first thing I'm going to do is I'm going to substitute 3 in. I'm going to subtract 10. I'm going to square that answer. And then I'm going to add 7. When I'm solving for y, I have to do all 3 of these steps, but I need to do the inverse of each of these operations. And instead of this being 1, 2, and 3 steps here, my order is reversed. So now, I'll have step 1, 2, and 3. So remember, I have to do the inverse of adding 7, which would be subtracting 7. And I'm going to do the same thing over here. So I would have x minus 7 is equal to the quantity y minus 10 squared. My second step would be to undo squaring something. So in order to undo squaring, I have to take the square root of both sides. So my square root and my square cancel each other out, so I have the square root of x minus 7 is equal to y minus 10. And because I only have the y minus 10 on this side, I can get rid of my parentheses now. So I'm done with my second step. My third step would be to undo subtracting 10, which would be to add 10 to both sides. And again, I like to put it at the end. So I would have the square root of x minus 7 plus 10 is equal to y. So the way that I would rewrite this is f inverse of x is equal to the square root of x minus 7 plus 10. Okay, and then the last one. Again, the very first thing that I want to do is I want to switch my x and my y around. So x is equal to y cubed minus 5. And notice I don't take the exponent with it, I only take the y. And the same thing if we were to look up here. I don't take the coefficient when I flip-flop these, I only flip-flop the letters. So I don't take the 3 with the x, I only take the x. The 3 and all the rest of the numbers stay over here, I only trade the letters. Okay, so my first step would be to undo the minus 5 here. So I would add 5 to both sides. So x plus 5 is equal to y cubed. And if you think back to what we were doing up here, if it was to the second power, we took the square root, which is basically the second root. So anytime that we want to undo a power, we have to do the nth root. So whichever exponent is here, the root has to match that. So this would be the cube root. And if I do the cube root on one side, I have to do cube root on the other side. So now the exponent and the radical cancel each other out. So y is equal to the cube root of x plus 5. And the way we would rewrite that is f inverse of x is equal to the cube root of x plus 5. Okay. So if the function transforms a to b is 1 to 1, then that means that the inverse of the function transforms b to a is also 1 to 1, which means that if you have the inverse of the inverse, it means you get back to your original function. So basically what that's saying is a function has to be 1 to 1 to have an inverse. Okay? This part right here is really important. What this is just saying is that your domain and your range change. So if you have an inverse, it means that the number in here is no longer your input, it's now your output. In a regular function, this is your input and this is your output. But in an inverse function, it means that this number here now is your output and this number here is your input. Okay? So here's what that means. All right. Given a table, what would the inverse table look like? Okay? So your inverse table would just flip-flop these two. So your input would now be your output, what your output was. 1, 2, 5, 10, and 17. And your new output would be what the input was previously. So 0, 1, 2, 3, and 4. Takes your input and your output and switches them. So they all just trade places. Same thing for your point. If your point is 3, 4, what is your inverse point going to be? All it does is take your input and your output and trade places. So your inverse point would be 4, 3. Okay. This is where it gets a little bit tricky, okay? If we have this as our function, what we want to do is find the following, okay? We want to find the function when your input is 2. So that means because we're not talking about an inverse, we're talking about the normal function, that means that this is our input. So we're going to take this and we're going to put it in for x, okay? This would be our x value here. We're going to substitute it in wherever we see x, okay? So we would have 2 minus 2, which is equal to 0. Okay? This one is talking about the inverse, which means that this now becomes our y value. We can think about this function up here as y equals x minus 2. So now, instead of substituting this in for x, we would substitute it in for the y. So we would have 0 is equal to x minus 2, which means that x is equal to 2, okay? So that means this is equal to 2, which makes sense because if our function of 2 gave us 0, our inverse function of 0 should give us 2. It switches your domain and your range, okay? If we have the inverse function, so we have the inverse of this function, and we want to find the inverse of 2, that means that we would put 2 in wherever the y value is. So we would have 2 is equal to x minus 2. To solve this equation, you would just add 2 to both sides. So x is equal to 4, which means that the inverse function of 2 is equal to 4. I can write that off to the side, that might be better. 0 is equal to x minus 2. If I add 2 to both sides, I get x is equal to 2. So that's where this 2 here is coming from. And this one is 2 would be y value. So 2 is equal to x minus 2. If we add 2 to both sides, we get x is equal to 4. Well, if this is the y, this is the x. So the inverse of 2 is equal to 4. This part right here just means if you have the function and an inverse, they basically cancel each other out, and your answer is just the input that you started with. Which also makes sense because if you started with 2 and then you did the inverse of that, you get back to your original function. Okay, that is the worksheet. It should be on the website. If you have any questions, email me, talk to me in class, and we'll see you soon.